So let me share my screen. Can you see my screen?
Yes.
Do you see the slides, please?
Yes,
Can you
we
still
can
see?
see them.
Okay. Okay. Thank you very much, Mr. Chairman, for giving me the opportunity to present some part of my research on concrete durability. So the presentation of today, the topic is durability assessment of low carbon concrete using electrical resistivity, chloride migration, and diffusion modeling. So when we say durability, as we are here, I can say we have laymen in terms of civil engineering. I can't say laywomen, sorry. What can I say? Is it laywomen or laymen? Because we have electrical engineering engineers, different part of engineers are here. So in terms of concrete, when we say durability, is the ability of the structure to withstand the specific design that is based on that is designed based on maybe to withstand, maybe it is designed in terms of corrosion environment or to resist the load or what is prescribed for the structure to maintain or to be resilient or to, that's what we call durability. That is structure to serve its purpose at the time specified for the structures. Let's say 100 years without any failure. When we say failure, sometimes maybe I can ask what is failure or collapse. Sometimes we misuse these words. So in terms of civil engineering structures, especially concrete, when we say failure, it doesn't mean collapse. When we say failure, the moment you see crack or deflection occurs on the structure, this means the structure fails. Whether it is 10 days, 20 days, or 50 years after construction. So there is difference between failure and collapse. Sometimes we misuse collapse as failure. So if cracks occurs on a structure, any crack that is like greater than 0.3 millimeters, that's the excessive crack, so the structure has failed. Or you see deflection, whatever it is, so the structure has failed. So we are trying always to avoid this. So what, like, there are many factors that cause failure and durability of structures. Among them, the most important ones are chloride ingression and carbonation. That is, what happens is corrosion, that is the corrosion of reinforced concrete inside the structure. Initially, concrete is high alkaline in nature with about pH about like 13 to 14 pH on pH scale. So that alkalinity of concrete provide a passivation layer, we call it passivation layer, a protective layer that protects reinforcement inside the embedded reinforcement that is still inside the concrete from corrosion. So when there is carbonation or some chloride get into the concrete above the threshold, that is 0.5% of the cement within the structure, so the corrosion starts in that structure. It will break the passivation layer. After the passivation layer breaks, then the corrosion starts. That time, we call the time that ingress or agents pass into the concrete, we call it initiation. After initiation, then the corrosion starts. We call that step as propagation. So now I want to discuss about the durability. As we know also, concrete is the most consumed substances over the world after water. Like every year, 30,000 or 30 trillion, sorry, 30 trillion cubic meter is consumed every year. This means every person here consume about 3.5%, 3.5 billion cubic, sorry, 3.5 billion tons of concrete. Every year we consume it. You consume it because more than the food that you are taking. When we say you consume it, because now you are living inside under a roof using concrete. So this means you are consuming it. When you are moving on a slab, maybe moving in your car, maybe the pavement is made of concrete. So this means you are consuming it. So now durability of reinforced concrete depends on how easily aggressive agents such as chloride ions, carbon dioxide penetrate into concrete and initiate corrosion. Traditional method of design, we use prescriptive method, that is using parameters. We use water binder ratio, cover thickness in design of concrete. But there are recent approaches. We concentrate on transport properties of the concrete. That is how these corrosive agents, like chloride, as I said, carbon dioxide, penetrate into the concrete and cause corrosion. So we design the concrete based on this, that is penetrability of this uh, agent. So electrical resistivity and chloride migration comes in because they have to pass through the concrete, through the porosity. So when the porosity or the concrete, it's not well connected, it has high tortuosity, the reagent or the corrosion agent cannot pass through it. So this is how electrical resistivity and chloride migration comes in. So we have supplementary cementitious material that is like waste product. We call there is GGBS. GGBS is a waste product from iron industries. We have fly ash, is a waste product from thermal power station. We have limestone powder, limestone from just limestone that we get from stones. We grind it, it forms limestone powder. Then there is a new concrete that we produce. We call it limestone calcine clay concrete. It is using like limestone and calcine clay. We use clay because there is a global warming. Global warming is caused due to cement industries. Like 8% of the carbon dioxide in the atmosphere is produced by cement industries. So we are always trying to remove or to reduce this cement from concrete. So in order to reduce this, we produce limestone calcine clay. It is normal clay that we use. We take it to the industry, we heat it. Actually, in producing cement, we heat limestone. That is what we call calcination. We heat the cement around 1600 to 1800 degrees Celsius. That is 1600 to 1800 degrees Celsius to produce cement. But with this clay, you can just heat it around 600 to 700 or 800. That is more than half of the carbon dioxide release can be reduced. So we produce this, we add limestone, we add what we call limestone, calcine, that is the clay that is heated. Then we add cement to produce concrete that is almost durable in the same with the same durability or close to that of ordinary cement. So this DDBS, fly ash, limestone powder, calcine clay can enhance durability of concrete and lowering the embodied carbon dioxide. That is what we are always after because of the net zero. We are always trying to reduce the amount of carbon dioxide in the atmosphere. So previous studies look at each test in isolation. They are using just, they are just not, they are considering binder chemistry, the type of concrete, the binder in it, the pore structure, and in this, we are going to combine this and interact them and see how they can predict the durability of concrete. So this study is systematically comparing Portland cement, that is ordinary Portland cement that produce 8% or 11% of carbon dioxide in the atmosphere with Fa, concrete containing fly ash, concrete containing GGBS, concrete containing limestone powder, and that of LC3, the one that I have already mentioned. The concrete, I use two water binder ratio, that is 0.5 and 0. Sorry. I use two different binder ratio, that is 0.4 and 0.55. and link resistivity-based diffusion with rapid chloride migration result to see how the durable concrete is. So the first objectives of this, that is to measure electrical resistivity of concrete. That is PC, low carbon, and low carbon concrete. When I say low carbon concrete, is the concrete using GGBS, LFE, the one that I have mentioned, with GGBS, limestone powder, LC3. So when I say low carbon concrete, as an indicator of post structure and durability. Then determine chloride transport resistance using NT builds and calculating migration-based diffusion coefficient. That is to see how this diffusion coefficient is a measure, is a unit that we use to see how concrete, how chloride can integrate or can pass through into the concrete, how easily it is. Then we estimate diffusion coefficient from resistivity using the formation factor method. There is a method that we create or we use to compare with the normal NT build and that's formation factor method to see how related they are, how close they are, sorry. So we used 12 concrete mixes using PC 100% Portland cement, the original cement that we used, the one that is used to produce high amount of carbon dioxide. Then we replaced 30% of the cement with fly ash. That's fed. Then the third mix, we replaced 30% of the fly ash and 10% limestone powder. The fourth one is 50% GGBS. We replace 50% of the cement with GGBS. Then we replace 50% with GGBS and 10% with LP. Then lastly, we produce LC3. In the LC3, the constituent are 50% normal Portland cement, 31% calcined clay, the clay that we heated, as I have mentioned before. Then 15% limestone powder, that is normal gravels that is grinded. Then 4% gypsum. The essence of adding this gypsum is to control the setting times of the concrete and also to reduce the effect of sulfate attack. So I use K value concept, FA 0.4 and GGBS. This K value is like when water is added to the cement, there is what we call hydration. That is, it will react with water and produce some binding material that cause binding properties to the cement and make it binded with the aggregate and everything and become hardy. So that is what we call hydration. So each part, like each cement have hydration. So when you add GGBS, there is a hydration that can reduce because the hydration, when we replace cement, it is the one that produce like after hydration. So sorry, when concrete cement react with water, hydration occurs. During the hydration, there is what we call CSH. It will produce in the concrete. Then what we call Portlandite. That Portlandite is a high alkaline in nature, and it is a part of hydration products. So when you replace the cement, this means you reduce the amount of hydration that will produce that Portlandite. So this means it will reduce the amount of Portlandite and reduce the hydration. So when we add FA, so we try to put some factor that will come and replace that hydration and replace the hydration that was removed by the fly ash. So that's why that's the essence of using this K value. This means we have to multiply or divide when we add 30% of fly ash, then we divide it by 4. This means we have to multiply the amount of fly ash by 2.25. 2.25, yes. For GGBS is 0.8. So we have to divide the amount by 0.8. This means multiply it by just 1.2. That is adding 20% of the GGBS in the concrete in order to compensate that hydration product that was removed from the cement. So then we use aggregate, that is crushed limestone, normal gravels that we use in Nigeria and everywhere. So we use millimeter.
Please, sorry to interrupt.
Okay.
The meeting will soon expire, so I've created another link and sent it to the chat. So everyone can join the new link once this one expires. Thank you.
So, okay, when did it expire? Is it in 10 minutes? Sorry, 3 minutes. So should I continue?
In less than 5 minutes, I guess.
Okay. So can I continue?
Yes, you can go, and once it expires, then you can enter through the new link. I've shared it in the chat box.
Okay. So then the type of aggregate that we use, like in concrete, we have cement aggregate, that is fine aggregate. We have coarse aggregate. Fine aggregate is the sand that we use. Coarse aggregate is like what you call gravels. So I use coarse aggregate, that is normal gravels that we use, that is crushed limestone, 4 diameter and 10 diameters, and then concrete sand, normal river sand. Then secondly, electrical resistivity was measured using 10 millimeter cubes of concrete with embedded stainless steel inside it. That is at 10 millimeter depths, 20 millimeter and 40 millimeter depths, different depths. But here I reported for 10 and 40 millimeter depths for easy explanation. Using SCR meter, there is a meter that used to measure electrical resistivity. The essence of measuring electrical resistivity is because chloride, when it passed through into the concrete, it used some ions. So it is taken by electrical resistivity, by electrical current, sorry. So when you test the electrical resistivity, you can test how fast, how if the concrete is have higher resistivity, this means it can resist the amount of chloride that will pass the concrete. So the higher the resistivity, the durable the concrete, and the higher or less corrosion that will happen to the concrete. So this is the essence of measuring electrical resistivity. Then RCM test, that is using rapid chloride migration test. There is a method that we call rapid chloride migration test, NT built 492. We conducted it using like a cylinder of 100 millimeter diameter with thickness of 50 millimeters to determine chloride migration. Then after the taking the test, then we use silver nitrate and test the depth of the chloride. So this is the arrangement. If you see this diagram, this is the arrangement of the stainless steel. These are the specimen A. This is the specimen, the concrete that is used. If you see, you can see some block with embedded fins inside it at different area. This is the LCR meter. This is the concrete connected with the LCR meter. So this is the diagram for rapid chloride migration test using NT-built. This is the specimen. As I said, it is 100 millimeter with 50 millimeter depths. So this is the machine that we pressurize the concrete. That there is a preconditioning that we do. Now here is where we put the concrete inside calcium hydroxide to spend some hours. This is where we keep it under pressure for some hours also. This is where we are taking the test. The below, the concrete at the down of the concrete is a